Black Hole Lab number 3. The purpose. The purpose of this lab is to create a computational model based on a given star trajectory that will calculate the net force with both the parallel and perpendicular components to determine the mass of the black hole. The importance. The momentum principle is applied to a theoretical example. Newton's law of gravitation is used, and we observe the effect of gravitational pull on one mass to another and how it affects their trajectory or orbit. The physics. So in this lab, we will be using the momentum principle, which is F net equals mass times acceleration. F net can also equal the change in momentum over change in time, which is roughly equivalent to dp dt. dp dt has both a parallel and perpendicular component, which we will use in this lab to calculate the mass of the black hole. dp dt parallel is equal to F net parallel, and dp dt perpendicular are equal to F net perpendicular. So F net, being the sum of the total forces, is equal to F net parallel plus F net perpendicular. We will also be using Newton's law of gravity, which is the net forces equal the gravitational constant times mass 1 times mass 2 divided by the radius squared. Mass 1 will be equal to the star, which is given, and it is 2 times 10 to the 30th, and the gravitational constant is 6.7 times 10 to the negative 10, and then the radius will be equal to the distance between the star and the black hole. And because the black hole is at the origin, it will just be equal to the position of the star. So to find the mass of the black hole, we will rewrite the equation to be F net times the radius squared divided by the gravitational constant times mass of the star equals the mass of the black hole. So the code. For the first part, we will be entering just the already known values, which is the gravitational constant, the mass of the star, and the change in time. We will also make edits to determine both the parallel and perpendicular component based on what we determine in the physics. And then we will make edits to the arrow scale so that it can properly depict what's going on, and to the position and axis so that each force is represented. And then lastly, we will edit so that the index represents the number of loops, and the mass BH is all of the masses of the black hole calculated together. I then divide the masses by the index to get the average mass of the black hole as mass. The forces and black hole were all printed. So these are my results. For the black hole's mass, I got 8.33 times 10 to the 33. For the F net, I got 8.03 times 10 to the 28th. For the F net parallel, I got 3.072 times 10 to the 28th. And for F net perpendicular, I got 7.43 times 10 to the 28th. And then to the side, you can just see the results printed, and then just me running the lab. So what does this mean? Discuss how the F net and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. So I basically am just going through how the change in momentum is really just the mass in motion, and the F net is the total amount of push or pull on the interaction. So while they may both be equivalent mathematically, they mean different things. So what if? So we have this scenario where basically we have all the same conditions, but we don't know the mass of this new black hole. So because we know that the mass for the star is going to be the same, the gravitational constant, of course, is going to be the same, and the distance is going to be the same because it is on the same path, the same orbit, the F net also has to be the same. So ultimately, based on this formula, we are not going to be able to know if the second mass is going to be different from what we calculated already. And that is it. So thank you so much for watching.